Hello everyone. Today we'll talk about the solution to the problem minimum obstacle removal to reach corner. This problem is not very difficult, since we only have to notice that, of course, since this is a grid problem, it might be useful to think of it as a graph and use some graph algorithm. And now we have to think about some classical graph problems and graph algorithms and see if some of them apply here. And indeed, some of them do apply here. In particular, the problem that we're given is simply the single source shortest path problem. This is the shortest path from 0, 0 to m-1, n-1. And of course we have to model it essentially as edges costing us something. But since we have an obstacle which we can remove, or an empty cell, we have to remove the minimum number of obstacles, then simply we can imagine that whenever we go into an obstacle, we have to remove that obstacle, and thus this is an edge that costs us something. And of course there is no point in going to the same obstacle more than once, because that means that we have a cycle. So we come into the obstacle, then we go somewhere else, then we return to the same obstacle. That means that if we remove the whole round trip that ended up at the obstacle again, we would still start at 0, 0 and end at m-1, n-1. So you can imagine that every obstacle can be entered at most once. So whenever we enter an obstacle, this costs us. If we don't enter an obstacle, this doesn't cost us. We can now use standard Dijkstra. We can use 0,1 BFS, which is a specified special variant of essentially Dijkstra, but in implementation it's more like a BFS, because this is a very simple case of Dijkstra. There are only edges that don't cost us anything and edges that cost us a fixed amount, which is the same for every edge. And also one way of doing it, which is the solution that I'm going to present, is to simply run a normal BFS. BFS, DFS doesn't really matter, but we maintain two data structures for our nodes. We'll be swapping between those two data structures, so at every step we pay another coin, let's say. So this represents nodes that can be reached by removing one more obstacle. We swap the two data structures with each other, and those two data structures represent the currently traversed empty cells, those that are currently being traversed, and the obstacles that are currently blocking our path. Because simply we can imagine that whenever we reach an empty cell, we of course want to reach all the other empty cells, and at some points we'll be meeting some obstacles, and now we can imagine removing all of those obstacles at once, and this leads us to paying one more coin, so increasing the result by 1, but allows us to reach somewhere further. And thus by swapping them, we essentially imagine removing all those obstacles at once. And of course it doesn't really matter, so because we can imagine it, if we reach some 5 different obstacles, let's say starting from the upper left corner, we reach 5 obstacles, then we can imagine that we remove them just by paying this single coin, because there is no point in an optimal solution to visit more than one of those obstacles. Because if we visit one and then the other, we could have immediately visited the other by paying the same amount, because they were reached at the same step. So the rest is just standard boilerplate BFS on a grid. We have directions up, down, left, right in whatever order we like. We have here a tuple of zipped directions, so now this will be the difference in row and difference in column. Remember height and width. We'll be keeping a set of visited nodes. And of course, since it's a BFS, we are using queues. Queues in Python are implemented as double-ended queues. We start at 0, 0. We don't have to add 0, 0 to visit it. We could, but we don't have to, since going between empty cells doesn't cost us anything. And the result is 0 at every step. And now, while there are still some nodes that we have yet to process, either blocked nodes or free nodes, we look at all the free nodes, and then we swap free and blocked nodes by increasing the result by 1. We take the next empty cell. For every direction we look at that direction, so we have row plus the difference in row, column plus the difference in column. We verify that they are within the bounds and that they are not yet visited, otherwise we continue. Now, if this is indeed the end, then we have our result. We can return it immediately. Otherwise, we add to our visited set the current new row and column that we're currently at, and we have to add it to the appropriate queue. So we append this pair to an appropriate queue, and the appropriate queue is determined by the value of grid at that position. If that grid is 0, we want cur. If that grid is 1, we want block. So we can just take the tuple of cur block, index into it by grid of nr and c, so 0 or 1, to give us the proper queue, and append the value to it. And we are guaranteed to reach the final position. We cannot break out of it, so this is in fact spurious, but indeed this is an infinite loop that we just know by specification it's always possible to reach at some point the final lower right corner.